Hi, my name is Jeff Perry, and I'm the manager of the WEBENCH team. Today I'm going to talk to you about an exciting new product from National, the WEBENCH LED Architect. First, I'm going to give you an overview of the solid-state lighting market. Then we'll discuss how to use WEBENCH LED Designer for LED and LED driver selection. And then we'll introduce and take a deeper dive into the new WEBENCH LED Architect tool. As you probably know, there's been a real explosion of applications for LEDs in many different areas, including general illumination, automotive, mobile devices, backlighting, and projection. In fact, in the WEBENCH design tool, we've seen a real explosion of designs for LEDs. LED and driver selection parameters. Let's get a brief overview of these. The first thing I'd like to talk about is the luminosity function. In other words, how do we quantify light from LEDs? So back in the early 1900s, scientists got together and decided what wavelengths of light the human eye is sensitive to, and they created a function called the luminosity function. And this measures the amount of light coming from any kind of illumination device that humans use to illuminate their world. And the units are luminous, I should say the output is luminous flux, and the units are lumens. So typically we'll measure the light output of lighting devices in lumens. This is a slide showing the different wavelengths of light coming from different LEDs in the WEBENCH tool. And as you can see here, and this is for colored LEDs obviously, what this is supposed to show is that one company's green is not necessarily another company's green, and particularly when you get into yellow, orange, and red, companies have different definitions of what those text values mean. So you really have to look at the dominant wavelength. And this shows you a dispersion of some of these wavelengths. Same thing goes for white LEDs. White LEDs are typically measured with color temperature. And color temperature ranges from 3,000 Kelvin up into the 7,000 Kelvin range for the lighting that we're talking about here. And so some people call the things in the lower level here, the 3,000, 3,500 warm white. The neutral white is in the middle, and then the cool white is on the right side. And so if you're looking at different whites, you have to be sensitive to the color temperature. Typical light output of lighting sources is presented here. So we have our 40-watt tungsten bulb, which has been the gold standard here for 100 years or more, and that outputs 500 lumens. If you want to go 100 watts, that's about 1,500 lumens from a tungsten bulb. Then we get into compact fluorescent lights, and so you can do 1,500 lumens with only 25 watts on that. A 55-watt halogen headlight will give you 1,500 lumens, and so on and so forth until we get down to the big 150-watt high-pressure sodium bulb, which is what's used in a lot of lighting fixtures on street lighting. And from that you can get all the way up to 16,000 lumens. So where do LEDs fall into this mix? This is a graph of LEDs in the WEBENCH tool. And these are approximately 1-watt LEDs. And so how much luminous flux can we get out of a 1-watt LED? Well, in this particular graph, we get all the way up to 140 lumens per watt. That's on the high side. And on the lower side, it goes all the way down to about 25 lumens for a watt of power. So you see there's quite a range of different values you can get with different LEDs. This is a chart of luminous efficacy, which is lumens per watt over time. And what this shows, and this is a study that was done recently, it shows that in 2010, we should be somewhere up around 120 lumens per watt for cool white. But in fact, recently, a company has announced 160 lumens per watt in 2010. So with the extensive R&D that's being done in this area, we're already surpassing the estimates that were present. Okay, so we see that one LED can give maybe 100 lumens or 140 or 150 lumens under optimistic circumstances, but in order to get the equivalent of a 100-watt light bulb, you're going to need 150, I should say 1,500 lumens. So maybe you're going to need multiple LEDs to do what you need to do. So how do we array these LEDs? Well, we can array them in parallel, put them side by side, which keeps the voltage low because the voltage of the LEDs does not add up. But if there is a slight difference in voltage for these LEDs, there may be current sharing issues. So some of the LEDs may get slightly higher current than others, and therefore they might be somewhat brighter, or their temperature would be higher. So there's a little bit of a trade-off there, and many people like to avoid using parallel LEDs on the same driver. So instead, they go with series. The problem there is if you've got 10 LEDs in series with 3 volts drop, you're going to have a 30 volt stack that you're going to have to drive there. And if your input voltage is lower than that, you may have to get into a boost topology or a buck boost topology, which can be a little trickier. Topology, we mentioned it there briefly. Buck topology is a step-down topology. The advantages of that are that it's simple and that the current requirements are relatively low because your output current, your input current is always going to be lower than your output current. However, it requires a higher input voltage typically because your minimum input voltage has to be above your output voltage. So if you stack up your LEDs, you got 30 volts on your LED string, you will have to have more than 30 volts on your input in order to do a step down. The boost, which can handle higher voltage on the output, it's a well-known topology, but it requires higher current. So if you have 10 volts in and you need to get 20 volts out, or in this example here, we've got 5 volts in, 14 volts out at 0.35 amps, with a 90% efficiency, you're going to actually require 1.1 amp on the input or on the switch in order to get 0.35 amps on your load. So boost can raise your current requirements and therefore call in to need higher current designs. A buck boost is something that can handle where your output is in between your input range. So if you've got, let's say, 10 to 20 in and 15 volts on your output, you can use a buck boost, but they tend to be a little more complicated and expensive, and so that's another option. Okay, let's talk about the WEBENCH LED Designer. Okay, an overview of this. It's got 4 steps. The first step is where you select your LED and your driver. The second step is where you would analyze and optimize your design. You're able to use SPICE simulation and calculate operating values over different current, or I should say different voltages. You can simulate it using SPICE, as I mentioned. And lastly, we provide for many of our parts, or some of our parts, I should say, the Build It feature, which allows you to get a custom prototype, and you can also get a design report. So here we are in LED WEBENCH, which you would get into by going to national.com and selecting the LED panel on the right side of that page. The first thing you would do would be to select your LED. And in this case, we show a blow-up of the screen. You've got an ability to select by manufacturer, color. There's also filters that you can use to filter by current, flux, and footprint. Here's a picture of the page where you have the LED selection. The criteria here, as I mentioned, are manufacturer, color, flux, current, and footprint. And so what you would do would be, let's say you want a white LED, you'd click on the white, and you would select from the list of LEDs. You also need to enter in your system specifications. And so one of the things is if you don't see an LED you like in the list, you can enter in a custom value, and you do that with this Configure LED panel, in which case you would enter in your operating current, your forward voltage, and your dynamic resistance. Then you need to configure your LED array. So in this tool, you are responsible for saying, okay, well, I need to have 5 LEDs, and I want them in series or I want them in parallel. And I will show you later the new tool takes care of that for you. But here in the traditional tool, you are responsible for that, and you're given control over that. You also need to enter in your V-in range, so your V-in min and V-in max. In this case, I've listed 24 to 32 volts, your ambient temperature, and then we also have an AC option if you wanted to do AC input. After that, you create your design after you've selected your driver, and you can view it. And this gives you opportunity to look at the operating values charts, graphs, bills of materials. You can simulate, you can have a custom design report, and for those that devices that have it, you can do the Build It prototyping step. We also feature little mini simulations for parts that have special features. For example, here we have thermal foldback, which enables you to sense the temperature of the LEDs and have the driver react such that it will pull the temperature, or I should say pull the current back, so that if the LED gets too hot, it'll cool itself off. Certain of our parts also have triac dimming, and so we allow you in the software to simulate what happens when you change the triac dimming angle. And last but not least, we have the WEBENCH design report, and what this gives you is a complete summary of your design, and that includes all the passive components needed for your driver, the bill of materials, and also the operating values charts. Okay, that tool has been around for several years, and you may or may not have already used that. What I'm going to show you now is the new WEBENCH LED Architect. This is a groundbreaking new tool, first of its kind on the market. No one else really has anything like this right now. And why did we do this? Well, what we just saw in the prior example was the LED behavior. We had a typical light output in lumens, and let's say the thing was at 140 lumens. The thing is that light output is only for 25 degrees C. And we don't necessarily always operate at 25 degrees C. Also, if we can increase our current, we can increase the light output and get perhaps more light out of the LED than the nominal. So if a LED is rated at 0.35 amps, maybe we can drive it at a half an amp, get more light out of it, and use fewer LEDs. So we see here the light output increases versus current. Light output decreases versus temperature. So as your temperature goes up, the light output's going to go down. So you can raise your current, increase your light output, but as your temperature goes up, the light output's going to go down. Also, as you raise your current, the efficacy decreases. Luminous efficacy, as we discussed earlier, is lumens per watt, or a measure of efficiency of the lighting source. The voltage increases versus current. And so in order to actually create a good design, you really need to model these behaviors to give your true light output. The trade-offs that are made here: high current gives you more light, so you can have fewer LEDs, but high current gives you higher temperature, and that gives you less light, and so you need to control that with a bigger heat sink. Then lastly, high current gives you lower efficacy, and so if you're running at high current, you may not be able to get your Energy Star approval. To show you this, I've got a graph here which shows the luminous flux, relative luminous flux versus current going through an LED. Now this is an LED that's nominally rated for 0.35 amps, and so you see there on the graph that you've got 100% of the output of light. Now if you take this thing and drive it at a half an amp, you can get up to 125% of your light output, and therefore for any given, let's say, amount of light that you need, you could use fewer LEDs, which is a good thing. However, as you're raising that current, you're going to raise your power dissipation, and as you raise power dissipation, the junction temperature goes up. So in this graph, we see the difference between running this thing at 25 C, which is where most of the data sheets characterize the LEDs. We're getting 100% of the light output. That goes up to 50 degrees C, we get 92% of the output, and if we go all the way up to 125 C, which this LED can operate at and still be okay, but we're only getting 70% of the light output. So that increase of 25% we got by increasing the current, we've now lost 30% because our temperature went up, and so we've actually had a net loss in light output. And so what do we have to do? Well, we need heat sinks. And this is a cross-section, a schematic kind of a block diagram cross-section of an LED. LEDs generate a lot of heat. Unlike incandescent bulbs, which radiate over many different wavelengths, including infrared, LEDs only radiate over their given wavelength, and so they got to get rid of the rest of their heat through conduction, basically out the back of the LED and into the PC board and the heatsink. What do you think the efficiency of LEDs is? Well, we know them as very efficient light sources, but if you actually look at the efficiency, which is the total amount of light that you get for your input power, they're only about 4% to 22% efficient using today's technology. So you're still losing maybe, let's say if they're 15% efficient, you're still losing 85% of your energy as heat, and you really need to get rid of that. And so we need to use a heat sink. As I mentioned earlier, the luminous efficacy, which is a measure of the efficiency, the lumens per watt, also decreases with current. And so in this particular graph, we see that as the current drops down, we can get up to 80 lumens per watt out of this particular LED. But as we drive this thing up at 0.7 amps, it's only 25 lumens per watt, which is pretty bad. Theoretical maximum efficacy for a neutral white light is 336 lumens per watt. So as we said earlier, decreased efficacy means no ENERGY STAR certification. So this is a balance that we're going to have to achieve here. Higher current maybe means lower cost, but worse efficacy. And if we want to have high efficacy, we'll probably have to lower the current and therefore use more LEDs. Okay, let's take a tour of the new LED Architect tool. This is the initial entry panel, and as I said earlier, you can access this by going to national.com and clicking on the LED panel on the right side of the page. You'll see up at the top a series of tabs. You would click on the LED Architect tab. At this point, we're going to go in and enter our LED requirements. We need to enter our input voltage for our driver source, our DC driver source or AC, enter in our ambient temperature, and then most importantly, we enter in the desired light output. And so in this case, we have 1,000 lumens. We also have a slider there for color. Now, if you're interested in becoming a little more, getting into some more advanced stuff, you can click on the Advanced Inputs button there, or link, and that gives you control over some other things. For example, if you wanted to limit your maximum output voltage, which is we do by default in the tool at 60 volts, you can do that here. Or if you say, well, I'm willing to go above 60 volts, because a lot of times 60 volts may be a safety threshold that if you go above it, you're going to need additional safety certifications, but you can give it your choice here on that. There's a checkbox for parallel strings on one driver. As I discussed earlier, there are some issues if you go parallel strings with current sharing, and so by default in the tool we do not check that. But if you do check it, oftentimes you can get away with fewer drivers. It gives you the ability to specify the maximum dimensions of your heatsink, specific LED manufacturers, and the maximum junction temperature that you'd want to go to. By default, that goes to the maximum allowed by the manufacturer for the LED. But if you wanted to increase the lifetime, for example, by lowering the junction temperature, you can do that here. Now that's going to get you probably into a bigger heat sink, and so again, there's costs that you have to pay. Okay, so now we've hit the Recalculate button under that LED Requirements panel, and we see the list of candidate LEDs here. This lists the LED part number, LED manufacturer. It lists a top view image graphic of the heatsink and a heatsink part number. And so we're dealing with real stuff here and real pricing, because we have pricing on many of these items. It also gives you the cost of the heatsink and heatsink and LED, and it gives you a measure of the footprint of the heatsink in square centimeters and the efficacy of the system. On the left side, there's a graph, and this shows you, gives you a real visualization of the choices in your LED selections. So on the x-axis, we have efficacy plotted in lumens per watt. On the y-axis, we have footprint, and that's typically the footprint of the heatsink, because the heatsink is almost always larger than just the LEDs themselves. Now, as you can see here, we've got certain things happening. If we go to the upper left of the graph there, we've got stuff that actually has low efficacy and high footprint, which is not real desirable. And as you go down to the right, we're starting to get into higher efficacy and smaller footprint. There's nothing that's deliberately in the right corner here, because that's the best of both worlds. And so typically what you'll get is either small footprint and have a compromise in efficacy, or you'll have a larger footprint when you go to the higher efficacy solutions. Additionally here, the bubble size is the cost, and so you've got a wide variety of costs here. The squares here are LEDs that we don't actually have costs on. Let's take a look at a couple of different options for 2500 lumens. In the top, we have one where we have 30 LEDs, and the efficacy is about 59.6 lumens per watt. It requires a relatively large heat sink of 257 square centimeters, and the cost is $63. If we go down to the one below that, there's an option where we have only 21 LEDs required. Efficacy is a little bit lower at 58.2, but the footprint is dramatically lower at 97 square centimeters. Cost, on the other hand, is higher, $109, so it's almost double the cost. So you can see here that there's many different ways to approach this problem with different types of LEDs and heat sinks. Okay, so once we've chosen the LED and heatsink array, using the tools that I just showed you, now we got to talk about driving the LED with the LED driver. So as I mentioned before, multiple LEDs can be hooked up in different ways, series or parallel. And we have different topologies, buck boost and buck boost. And so how do we say which one of these is the best? Well, after we click the Select LED button, we get into a page that shows us the driver options. And so here what we see is the system metrics, including not only the LED array and heatsink, but also the drivers. And so you can see here that there are multiple different driver solutions, each with a different cost and efficacy. Okay, so this is a graph here. On the x-axis, again, we have system efficacy in lumens per watt. On the y-axis, we have the footprint of the heatsink and driver. And I have this highlighted here with some buck and some boost options. And so this is not necessarily always true, but in some cases the buck may be cheaper, or in some cases I've seen the boost be cheaper. And same goes with the efficacy. There can be different scenarios here for different LED arrays. But in any case, you can see here, pick out right away, if you want high efficacy and small footprint, you're going to want to be down in that lower right corner if possible, and keep an eye on your bubble size for your cost. Okay, when we're talking about LEDs right now in the current market, the LEDs really dominate the design in both area required and cost. So this is an example here where we've got a 2500 lumen system, and in the top there we've got 12 LEDs plus the heat sink, and they're taking up an area of about 257 square centimeters, and the cost is $61.59. The drivers required to supply power to that, we're going to need 2 of them. They only take up 7 square centimeters, and the cost is $5.26. And so right now, like I said, it's really the LEDs that dominate this design. Okay, after you've picked your driver, it flips you into the LED Architect LED WEBENCH design tool. And here you've got access to the traditional things that I just talked about. On the right side, you've got simulation and other operating values, schematic, and BOM. And on the left side, you've got a panel that shows on the bottom there the LEDs arrayed on the heatsink. Above that, you've got the LED block diagram. And then finally above that, you've got the system level parameters that we talked about, the system footprint, system BOM cost, and system efficacy, and also your heatsink parameters. And so at this point, you can fine-tune your design. You can go in and do component changes and optimize it even further. And then you've got your LED and driver design. Okay, in summary, the WEBENCH LED Designer is a powerful design tool for more advanced customers, and that's the first thing that I showed you, where you actually go in and you select the LED, you array it yourself, but then you're allowed to go in and select the driver and optimize it using the WEBENCH tools. The new tool that we introduced here is the new WEBENCH LED Architect. This is targeted toward lighting customers. It considers the LED behavior over temperature and current, and also the heatsink properties and the heatsink that's required. Provides the driver configuration and topology, so you can look at different topologies and do cost-benefit trade-offs based on size, cost, and efficiency. And so overall, in summary, hopefully what we've seen today is that WEBENCH saves you time, And I encourage you to use WEBENCH for your next design. Thank you.